Okay, we're going to review the regions of the periodic table. Now this is an outline of periodic tables. We've got about 5 or 6 of them. No, actually got 7 or 8 of them. And what we're doing here is we're taking the big periodic table and we're making just an outline to see some patterns here. Okay? One of the patterns is representative elements. Now there's nothing really special about that except the only reason we want to know about representative elements is that we're trying to figure out electron structures for atoms. In high school, we mostly stick with the elements in these 2 regions right here, the representative elements. That's all that's about, okay? Then, we also did a periodic table where we looked at orbital regions. Now, we're going to spend a lot of time with this in the remainder of this unit. This is really, really, really important. So, S sublevel regions are here. All the atoms in this region represent the filling of electrons, or the placing of electrons in an S sublevel. All the atoms over here represent the placement of electrons in the P sublevel in the highest energy level. Helium doesn't belong there, it belongs over here, at least when we're talking about orbital regions. This is the D sublevel region and the F sublevel region. Okay? Alright. Then we also talked about, you should have a periodic table outline, where we looked at metals, non-metals, and where the metalloids are located. Okay? Metals, non-metals, and metalloids. Now, you should have this already. I'm just going... Oh, I didn't move the H over? Okay, then let's make sure we're clear on that. Hydrogen up here doesn't belong with the metals. Hydrogen's not, at least on this planet, not considered a metal. I say on this planet because there theoretically are conditions where hydrogen might actually act like a metal. We don't need to know about that, okay? But if you were near the rocky surface of the planet Jupiter, hydrogen might actually behave like a metal. Okay? But for us, it behaves like a non-metal. We're going to put it over here next to helium. You got that? Alright, now, families and groups. We don't need to know every single family by special names. We need to know some names about some family. So this first column here is the alkali family. No? We didn't do this?
Oh, yeah, but...
I didn't name it. Families and groups.
Yeah.
These are the families and groups. We've got the alkali family in the first column, except hydrogen is not part of it, because these are actually metals here. And so hydrogen is not really a metal, so we treat it like it's not part of the alkali family, although it has some chemical behaviors that are similar. Alkaline earth family, or alkaline earth metals, here. Over here to the right, we've got noble gases on the far right. Halogens next to that. Any of these columns right here, that's fine, that's what I'm getting to. Any of these families right here, we simply name those according to the element at the top. So the first column is the boron family, and the carbon family, and so forth. Okay? Then the transition metals are in here, and intertransition metals down here. Alright, we're just doing a quick review. Now, atomic size. We said that as you go to the right, across any row of the periodic table, atoms get smaller. As you go from left to right, physically, the diameter or radius gets smaller as you go across to the right. As you go down in any column, in any family or group, they get larger. And what's missing from this, apparently, is because when I made a photocopy of this, the line apparently didn't copy. Let's see here. Is that means that the largest atoms are in the upper right, the smallest ones in the lower left. So that's what that smaller and larger thing is all about. Okay? Now, electronegativity. This is going to be really, really important when we get to bonding in a couple of units from now. Alright? Several units from now. So, the pattern of electronegativity, and electronegativity, we said, is all about sharing electrons. It is the relative force with which one atom pulls on a pair of electrons it shares with another atom. That's what electronegativity is. Since noble gases don't generally bond or share electrons, then we're going to leave those out. You have to leave out the noble gases to understand the pattern. So the smallest or least amount of electronegativity is in the lower left. We're down here where cesium and francium are located. And the largest is up here in the upper right. except for the noble gases, and that's where fluorine is located. All right? Now,
Hold up.
you don't have this one already? Well, I sent this to you by email. You should all have it on your email. And I don't really have time to stop very much here. If you're just kind of touching up something, that's one thing.
Smallest? All right, I got that.
All right, now, then we went to first ionization energy. Now, ionization energy and electron affinity are about not covalent bonding. Electronegativity is about covalent bonding. Ionization energy and electron affinity are about ionic bonding, and they're kind of like two sides of the coin. Ionization energy is the energy you must put into the system. In this case, the system is the electron cloud of an atom. Ionization energy is the energy you must put into the electron cloud of an atom to remove electrons. Okay? So first ionization energy is the energy that's required to remove the very first electron from an atom. And so the pattern then is it's highest here. It takes more energy to remove the first electron from helium than any other atom on the periodic table, any other element on the periodic table. And the lowest is down here with cesium and francium. Okay? Electron affinity then is the other side of the coin. If this is how much energy it requires that you put into the electron cloud to remove an electron, this is the energy that's given away when you put another electron on it. Alright, so noble gases don't want extra electrons, so we leave those out of the pattern. They virtually have no electron affinity because they don't accept any extra electrons. They're done. They're finished. But fluorine gives you the greatest amount of energy out when you put an electron on there. It's the highest. Cesium and francium have the lowest amount of energy given out when you put an extra electron on it. And that's a general pattern there. Okay? So all of these are important, but the one that we're going to spend the most time with right now is the orbital regions. So if you don't have that out, you need that out and your periodic table, and we're going to start talking about drawing orbital diagrams. Not orbital diagrams.